and gentlemen, welcome to the third talk of this session. The speaker is Jeremy Sakstein from University of Hawaii at Manoa. He is an expert in testing theories of gravity, dark matter, dark energy using astronomical observations of stars, black holes, and gravitational waves, and is going to talk on the speed of gravity and the fate of dark energy for the next hour. Please join me in welcoming Jeremy Sakstein.
Thank you. Okay. Let me start by thanking the organizers for creating such a wonderful conference. I'm really honored to receive a Frontiers of Science Award, and I'm also very humbled to share the stage with so many accomplished scientists. I'd also like to mention my collaborator in this work that I'm going to tell you about, Professor Bhuvnesh Jain at the University of Pennsylvania, who unfortunately couldn't make it to Beijing to receive the award with me. So let me start by telling you a bit about myself. My name is Jeremy Sakstein, and I'm a theoretical cosmologist. And so that means that I spend my research time trying to understand the origin, evolution, and fate of the universe. So what do we know about the universe? Well, in 2025, we think that we understand a lot about the universe. We think that we understand the universe from its first instance, around here, all the way to today, 13.8 billion years later. And each of these panels here represents a different interesting epoch in our universe's evolution. And I really wish that I had time to talk to you about all of them, but I don't. So I'm going to focus on the stage of evolution that I'm most interested in, which is the late universe, so this region labeled today. And for me, this is a very interesting time, because if you look at the past, the recent universe, you can see that we've very recently entered a phase of what's called dark energy, or an epoch of accelerated expansion. So we think that at the current time, the expansion of the universe is accelerating. And if you stop and think about it, this is actually a very surprising thing to observe. And in fact, it's so surprising that after its discovery in 1998, the discoverers were awarded a Nobel Prize in 2011. So why is this such an amazing and unexpected discovery? Well, if you stop and think about it for a moment, we think that the dominant force in the universe is gravity. And we know from our everyday experiences that gravity is an attractive force. It wants to pull everything together. So it's a little bit surprising that when we look out onto the larger scales in the universe, there's something out there that's pushing the universe apart. This counteracts just our common sense intuition about what gravity is and what gravity does. And by now, the evidence for an accelerating universe is everywhere. We see it in all of our observations. So we see it in the cosmic microwave background, which is light left over from the Big Bang. We see its imprints on the gravitational lensing of light. So as light passes a source and is gravitationally lensed, the expansion of the universe affects that, and we can see that the universe is accelerating. We see it on the formation of cosmic structure, things like galaxies and galaxy clusters. And we also see it in the apparent brightness of type 1a supernovae, which are the explosions of long dead stars. And in fact, this is how dark energy was first discovered. So what's causing this acceleration? What is it out there that's pushing the universe apart? Well, we don't know, but we've given it a name, and we call it dark energy. And in cosmology, dark is really a synonym for we don't know. We don't know what it is, but we want to characterize it, and the first thing you do when you want to characterize something, you give it a name. So we call it dark energy. But what we do know about dark energy is there's not a little bit of it, there's lots of it out there. And if you look at this pie chart, which is a census of the contents of the universe today, perhaps the most striking feature is that only 5% of the universe is in regular visible matter or standard model matter, the stuff that everything in this room is made of, this table, my clicker. 25% or so is in the form of this invisible dark matter, which you've probably heard about, but I won't have time to talk to you about today. And a whopping 70% or so is in the form of this weird, mysterious stuff called dark energy that's sitting out there, pushing the universe apart. So this is what I spend my time studying. I want to understand what is underlying physics or the mathematical description of dark energy. So this is a very expansive topic, and it's a very expected discovery, so it's nice to have a guiding principle to try and figure out what dark energy is. So to try and motivate what I'm going to talk about, I like to recall this quote from John Archibald Wheeler, who was one of the pioneers of general relativity. And Wheeler famously said that space-time tells matter how to move, and matter tells space-time how to curve. And when you think of it along those lines or through that lens, there's only really two possibilities for what dark energy could be. So number one, there could be some type of new matter out there that's telling space-time how to curve, some type of negative pressure fluid. The other possibility is that maybe gravity itself is modified. So maybe general relativity breaks down on very large scales, or it needs some type of correction. And this modification of general relativity, our best theory of gravity, is modified so that on very large scales, the universe pushes itself apart. So I've worked on both of these possibilities throughout my career. And again, I wish I had time to talk to you about both of them because they're really, really fascinating and interesting topics. But I'm just going to talk to you about the second possibility today, just because that's where my FSA work fits into it. Try and explain dark energy with modified gravity. You immediately run into a problem. And that is that we have tested general relativity so precisely on so many scales that it's actually very difficult to find theories of modified gravity that can simultaneously explain the cosmic acceleration while also satisfying these other tests on smaller scales. So one example of this is binary pulsars, and we've just had a wonderful hour-long talk about these objects, so I'm very grateful that I don't have to explain the physics in detail. But here they are again. These are these binary pulsars, so they're neutron stars, which are the cold, dead remnants of massive stars after they explode. These cones are very strong magnetic fields, which, as we've heard, we can use to detect these. And as these neutron stars orbit each other, general relativity predicts that they're going to emit gravitational radiation, so they're going to lose energy. Their orbital radius is going to shrink because of that, because you're losing energy. And this is something that we can predict. So what I'm showing here is this famous Taylor pulsar that we just heard about. So on the left, I'm showing the shift in the periastron, which you can think of as a proxy for this effect as a function of our observing year. The black solid line is Newtonian gravity, so non-dynamical gravity, and in this case, there's no radiation, so we wouldn't expect a change. The blue line is the prediction from general relativity, and these red dots here are our observations. So as you can see, our observations of this system fit the general relativity prediction extremely well. So it's if you have a theory of modified gravity, you somehow also have to be able to explain this prediction. Another place we've tested gravity very well is in the solar system. So if you change the theory of gravity, you change how gravity works in the solar system. So here's an example here. It's the famous perihelion advance of Mercury. And generically, you'll predict what we call fifth forces, so modifications of Newton's law of gravitation and its relativistic extension. And what I'm showing here are the various laboratory and solar system tests of general relativity that we performed in the solar system. So on the bottom, I'm plotting the range of any new or additional force that could be there due to modified gravity. And on the left, I'm plotting the strength of this force relative to Newtonian gravity, so Gm over r squared. And I think that the real telling thing about this plot is the axis here. So if you look at the left axis, you can see that this number starts at 10 to the minus 1 and just gets smaller at 10 to the minus 3. So any fifth force in the solar system is constrained to be something like 1 part in 1,000 compared with the Newtonian prediction. It has to be 1,000 times weaker than Newtonian gravity. And this was the real stumbling block for modified gravity, because how could we possibly have a theory of gravity that's subdominant to general relativity in the solar system by a factor of 1,000, but yet somehow dominates the universe on large scales? This is very difficult. So this, for a long time, seemed to be a bit of a stumbling block, and maybe it was a bit of a no-go for modified gravity. But the situation changed in 2003 or so with the discovery of something called screening mechanisms. So before I tell you what screening mechanisms are, I'm just going to motivate them conceptually. So if you think about general relativity, it's a beautiful nonlinear theory of gravity that predicts a vast array of different phenomena across different scales. So on very, very small scale, you get very strongly gravitating objects like black holes and neutron stars. On intermediate astrophysical scales, you get things like planets and stars and galaxies. And on the larger scales, you get an expanding universe. So maybe the resolution in modified gravity is the same thing. Maybe there's some kind of non-linearity to this modification of gravity that makes it look like general relativity on smaller scales while still explaining dark energy and the cosmic acceleration on cosmological scales. And so this is the idea with screening mechanisms. And the way they work is the modifications of gravity depend on the ambient density. So the idea is that in low densities, that something like the cosmological vacuum, the fifth force emergence drives the cosmic acceleration. But at high densities, things like the solar system, things like neutron stars, everything goes back to looking like general relativity. And these are some really great mathematical descriptions of these theories, but I'm just going to talk about them conceptually. So if I think about the density of my system increasing this way, at very low densities, we have cosmology, and so this would be unscreened. The modifications of gravity would appear. At very high densities, we have things like the solar system, and the modifications would disappear. And then in the middle, we have this kind of intermediate regime of astrophysics where we might have some novel effects that we could look for. And this is actually where I spent most of my career working. I wanted to look for signatures of screening mechanisms and try and detect dark energy by their effects on astrophysical objects. And there are several proposed screening mechanisms out there, but I'm just going to talk to you about one. This is the most ubiquitous screening mechanism. So we have a general theory of modified gravity that could have been dark energy, and every single one of them, with a couple of exceptions, exhibited something called the Weinstein screening mechanism. The Weinstein screening mechanism is a very complicated nonlinear mechanism, but it's really nice and simple to describe in pictures. So if I take a theory with a Weinstein mechanism, and I take an object like the sun, and I think about how far away I am from the sun, which is this white arrow here, in screen theories, there are two regimes. So I can draw a line here at something called the Weinstein radius, and this is a new length scale which depends on actually the mass of this object, which appears in these theories. And in Weinstein screening, things are very simple. If you are inside the Weinstein radius, everything is screened, there are no fifth forces. If you are outside the Weinstein radius, everything is unscreened. So cosmology, of course, is outside the Weinstein radius of the collapsed matter in the universe, and so the acceleration can be driven that way. And if I just take a general theory of dark energy that can exhibit the Weinstein screening mechanism and take an object like the sun, the Weinstein radius naturally comes out to be about 100 parsecs. So if you have a theory with Weinstein screening, you have, by virtue of the sun being there, you automatically satisfy all of your laboratory tests, all of your solar system tests, and objects like neutron stars are also highly screened. So this was where we were in 2017. We had this really great theory called Weinstein screening, and now we had this really great theory. We wanted to know, can we test it? Because, we want to discover dark energy. So we were very interested in how we could test the Weinstein mechanism. But here we run into a bit of a problem. And it's in fact the opposite of the problem that I showed you before, because the problem with regular or classical modified gravity theories is that they're incredibly highly constrained. Now, the problem with Weinstein screening is that it's so efficient, there are practically no constraints at all. So again, I'm showing you the same plot as I did before. The left-hand side is still the relative strength of the fifth force to Newtonian gravity. I've changed the bottom a bit just to be theory specific. So this RC is a new parameter that shows up in Weinstein screen theories. And it turns out that the best constraints on Weinstein screen theories came from 1993, when people were taking data and shooting lasers at the moon, so something called lunar laser ranging, to try and test gravity. And this was a long way away from where these dark energy theories live. We needed to prove over here and try and rule out, or at least test into the region over here. And as I alluded to, Weinstein screen theories are really hard to test. Everything is screened. The solar system, that's screened. Stars, they're screened. Galaxies are screened. And pulsars are screened. So we had to kind of go back to the drawing board and really come up with some inventive ways of trying to test the Weinstein mechanism. How are we going to test it if everything's screened? So around 2012 or so, these two researchers proposed a test, and it involves something called the strong equivalence principle. So I'm just going to tell you what the strong equivalence principle is. The strong equivalence principle is something that's kind of hardwired into general relativity, and it's actually something that comes out of general relativity, even though we refer to it as a principle. But essentially, it says that the gravitational motion of a body or an object does not depend on its self-gravity. So what does this mean? Well, let's suppose I take say a fixed source, something like a supermassive black hole, and I imagine a solar mass non-relativistic object like a star around this supermassive black hole, or an object of the same mass but that's relativistic like a solar mass black hole. Both of these will fall at exactly the same rate. If I drop them, they will experience the same acceleration. There's no, you're insensitive to whether it's a black hole or a solar mass star, so you're insensitive to how strongly gravitating this object is. And this is a very important principle because you can classify your theories into whether they satisfy the strong equivalence principle or not. So I've got a little comparison table here. Theories which satisfy the strong equivalence principle are general relativity, and theories which don't satisfy the strong equivalence principle are basically everything else. So it's a very unique prediction of general relativity that the strong equivalence principle is satisfied, up to a few caveats that I won't go into. Pretty much every other theory of gravity that is studied, at least everyone that's taken seriously, is one that violates the strong equivalence principle. So what that means is we can try and test whether gravity is general relativity or not, and in particular the Weinstein screening mechanism, by doing these Galileo-type experiments where you take things like black holes and stars and throw them off the leaning tower. So here's the test that was proposed. Let's suppose you take the leaning tower, but you don't throw a black hole. Let's suppose you throw a galaxy, and most galaxies have a supermassive black hole at their center. Now, as this falls in the gravitational field of the Earth, there's going to be two contributions. There's going to be a contribution from general relativity, and there's going to be this extra contribution from the Weinstein field, or this extra Weinstein. But this black hole is not going to feel that second contribution. This is the violation of the strong equivalence principle. And I don't have a lot of time to go into that, but essentially black holes are subject to something called the no-hair theorem. And this no-hair theorem essentially means they are insensitive to a lot of the extra types of particles that are needed to modify gravity. So black holes only feel general relativity, at least at this level, and the stars and gas in the galaxy will feel both forces. So that means as this thing falls, the black hole is going to lag behind the center of the galaxy now because it's not falling as quickly, and eventually there's going to be some extra force pulling it back towards the center from the stars at the center, and so you're going to get a fixed offset. So this is ultimately what the strong equivalence principle does. It creates offset black holes in galaxies. So I should say this is actually true for any theory of modified gravity, but you would usually never perform this test because we have all these really precise experiments and these really precise binary pulsars for offset black holes in galaxies. Well, as I said, the Weinstein mechanism can't be tested with these other experiments, so this ended up being the strongest test of these theories. Now, in real life, we don't have a leaning tower that we can throw a galaxy off, but we have something called galaxy clusters. So this is a big group of galaxies, and I've drawn an illustration here. So here's a big cluster of galaxies, and typically you get a few satellite galaxies which are falling towards the center in the external gravitational potential. And so the idea is you would look for these offset black holes in the galaxy. So the one system that we looked at is called M87, which is a galaxy that's falling towards the center of the Virgo cluster, and there's some pretty good observations of these. It's difficult to see here, but this is just a picture of the galaxy cluster. And so what we did was we came up with a model for the Virgo cluster that includes modified gravity effects. We modeled this cluster under the influence of modified gravity. So let me show you what I'm plotting here. On the left, I am plotting the force on the satellite galaxy due to the cluster. And on the bottom, I'm plotting essentially the distance from the center of the cluster, but normalized to some helpful astrophysical quantity. The blue is the general relativity force. And then if modified gravity were there, I'm showing two different possibilities. For models that are not dark energy, that's this red curve. And for models that are dark energy, that's this black curve. So as you can see at some radius, and in fact, this is the Weinstein radius, there's a component of the force that's largely dominated by modified gravity, and this would lead to an offset black hole in M87. So now using this model, we could go ahead and calculate the predictions for this offset. And of course, it's astrophysics, so there's a few uncertainties that we had to include. So each of these curves here are the offset in kiloparsecs as a function of satellite distance from the center. And these are just different models. So if you look at the plot here, the spread's about a kiloparsec or so. But you're looking for about a kiloparsec offset with this test. So it turns out that to very high precision, the black hole in M87 is not really offset. I think it's something like 0.03 arc seconds or something like that. And so we were able to obtain these new bounds. Of course, we hoped to detect something, but we didn't. So again, fifth, fourth strength versus model parameter. The red dashed line are the old bounds from 1993. And as you can see, we were able to extend those bounds quite a bit and even start pushing into dark energy models. But this was not enough. We still had this region of parameters where the Weinstein mechanism could account for dark energy. So we wanted to try and probe into that region. So where can we go from here? Well, this is where we were. We were here in 2017. We wanted to look for new tests of the Weinstein mechanism. And we were a little bit stumped. But 2017 was a really landmark year because, as many of you know, there was a very amazing gravitational wave detection that year. So it turns out that you could use gravitational waves to test the Weinstein mechanism. It's just we thought that we were further away from doing that than we were due to this landmark detection. So let me tell you a bit about gravitational waves, what they are, and how they fit into this whole picture. So when two very relativistic objects are in a binary, as I said before with the pulsars, they will emit energy into gravitational radiation. And here's a simulation of this thing. So what I'm showing here are two black holes which are orbiting each other. And as they orbit each other, they lose energy due to angular momentum. The orbit shrinks. And as the orbit shrinks, the system gets increasingly relativistic. The amplitude increases until eventually these black holes merge to form a single object, which is going to happen in a second. And they shoot off a huge pulse of gravitational waves. And we're now able to detect these, and I'll show you how to do this. In a second, there we go. There's the merger. And so you're left with a single black hole and this huge release of gravitational waves, which you can think about as ripples in space-time or waves in space-time. So how do we detect these things? Well, let's see what happens when these waves hit Earth. So here's a system again, gravitational waves. And when they reach the Earth, you can see they distort it, they stretch the Earth, and we can try and look for this distortion. The way we do this is gravitational wave interferometers. And here is the first one. It's called LIGO, the Laser Interferometer Gravitational Wave Observatory. And I'll show you how it works. So this is a laser, two-way mirror splits it, hits these mirrors, bounces back, and hits there. And as a gravitational wave goes past, because it stretches the space-time, you see the mirrors jiggle, and you get this change in the path length. Here's a more detailed view. So as the laser comes through, hits this mirror, bounces back, then it's going to be recombined by this beam splitter. And as you can see, it's out of phase, so there's no signal here. So you don't detect the signal, except when a gravitational wave comes past, it changes the path length, and now you can see suddenly they're in phase. So suddenly you can see, you're going to get a change in the amplitude of laser light here, and you can see it showing up there. Okay. So you see it's kind of similar to these classical interferometer type experiments. And right now, work of these, so we have two in the United States, LIGO Hanford, LIGO Livingston, Geo 600, and then Virgo. There's Kagra in Japan, and LIGO India should be operational by the 2030s, I believe. But back then we only had three. We only had LIGO Hanford, LIGO Livingston, and Virgo. So here's the first discovery of gravitational waves. They were predicted in 1915. So it's been 10 years since we've discovered them now. Nobel Prize in 2017 for these three people. So it's a merger of a 36 and 29 solar mass black holes. They ended up forming a 62 solar mass black hole. And the numbers involved are incredible. It's amazing that we can detect these things. This thing happened 1 billion light years away, and the amount of energy released into gravitational waves was via E equals mc squared, 3 times as much as the mass of the sun. So crazy amounts of energy. Okay, so now I've told you what gravitational waves are for a few minutes, and you're probably sitting there thinking, well, what do gravitational waves have to do with dark energy? So let me tell you about that. So general relativity makes a prediction for the speed of gravitational waves, and that is that they travel at the speed of light. Many theories of modified gravity, including those that exhibit the Weinstein mechanism, make a different prediction. They predict that the speed of light is not equal to the speed of gravity. And if you have a theory that exhibits the Weinstein mechanism that also makes this prediction, which is the majority of them, this difference in speed is not small, it's large, it's order 1 or so, and I'll come back and talk about that in a minute. So maybe we could test the Weinstein mechanism by trying to measure this effect. So here's the first equation of my talk. It's speed equals distance over time. And so you need 4 things to measure this effect. Number 1, you need a source. You need some source that produces both light and gravitational waves. You also need to be able to measure the gravitational waves and their arrival time. Similarly, you need to be able to measure the light and their arrival time. And then finally, you need a distance to the event. And this one turns out to be the tricky one, because this one, as you'll see in a minute, it's very hard for LIGO to localize these events. Their sky localization is not very good, and that's because you only have 3 detectors. It's harder to figure out where these things came from. So let's go through each of these and talk about how we can find one. So the source has to be something that we've heard about in the previous talk, which are neutron stars, and that's because black holes, or at least most merging black hole systems, are not expected to produce light. So we need something that will, and so we're going to produce them using neutron stars. So let me just stop and tell you a bit about neutron stars, because these are really, really fascinating objects that I think deserve a slide. So neutron stars are the dead remnants of very massive stars. So when very massive stars explode, they leave behind these cold stars. And they're really, really hard to get your head around, because they have densities and pressures that just can't be replicated on Earth. So to try and put this into context, if you were to take a teaspoon, dip it into a neutron star, and weigh it, that teaspoon would weigh 10 million tons. And they're also very strongly gravitating objects, and they're not black holes, they're made of matter, so when they collide, they produce very large explosions that you can see in light, and because they're strongly gravitating, they will also produce gravitational waves. So these are really, really crazy objects. They have masses of order the sun, so 1.5 solar masses or so, but only 15 kilometers in radius or so. So to put that in context, that is an object with the mass of the sun in the distance from where we are now to the center of Beijing, to the Forbidden City. So that's how crazy they are. So it turns out that in 2017, we measured a landmark source that was 2 merging neutron stars, so a binary neutron star merger. And this event really did change the world. A lot of different science came out of this one event. I only have time to tell you about the pertinent science, of course, but it really was a landmark discovery. So let me tell you about it and how it fits into this picture. So as I said, typically you can't localize gravitational waves. So here's a picture of the localization of some gravitational wave events. And as you can see, they're pretty large on the sky, except for this one, 1708-17. So why were we able to localize this? Well, it turns out we had some extra information, because it just happened to be in Virgo's blind spot. So here's the signal in LIGO Hanford, that one you can see clearly, this one in Livingston, but nothing in Virgo. And of course, we try and minimize blind spots. We keep them as small as possible because we want to detect everything. So the fact that this was in Virgo's blind spot actually helps you localize it a little bit better. And it was actually localized to a galaxy that we know. So it's localized to a galaxy called NGC 4993. So here are two images of the same galaxy. This one was taken in April 28, 2017. And if you look at this arrow, nothing there. Here's the same image on August 17th. And as you can see, there's a very clear distinction. You can actually see this, this event happen in these photographic plates. Sorry, not photographic plates, in these photos. And here's the event now. So this is the NGC 4993, and you're about to see two neutron stars. And when they merge, they're going to produce the gravitational waves you've seen before. Here they are. And they're also going to produce a huge explosion in light. There it is. It's called a kilonova. Great science will came from it, but again, don't have time to tell you about it. And we were able to observe both of them. So it released gravitational waves and light in the form of gamma rays and X-rays. And here's the detection. So top one is Fermi, which measures the light. This is LIGO. There's the gravitational wave detection. And wait a little bit. There is the gamma ray burst detection there. So we were able to detect both of these signals. And importantly, now you can measure the difference in timing and use that to constrain the speed of gravity. So the difference in the timing was about 1.7 seconds or so, give or take, error bars. So what does this mean for the speed of gravity? Well, let's see. So here's our signal. We know where this event was located. It was located in NGC 4993, which was 130 million light years away. We have other observations of that galaxy that let us determine the distance. So all I need to do is rearrange speed equals distance divided by time to calculate the change in the speed. So c is delta t, d divided by delta t. If you plug that in, you get a crazy strong constraint. You find that the difference between the speed of gravitational waves and the speed of light, normalized to the speed of light, is 1 part in 10 to the 15, absolutely tiny. So with such a strong constraint, it turns out we were actually able to exclude a large region of dark energy theories. So let's see, where are we? So here's an example which I'm giving. This is something called quartic Galilean dark energy. And if those words don't mean anything to you, don't worry. This was kind of the quintessential paradigm for Weinstein screens, amplify gravity as dark. So what I'm plotting here on the bottom is the one free model parameter in this theory. And on the left, I'm plotting the log 10 of the dark energy fraction. So if this thing can be 100% of dark energy, it's up here at 0. And if it could be a subcomponent of dark energy, it's down here somewhere there. And the combination of both of these tests that I told you about, the supermassive black hole test that we worked on, and now the speed of gravity, rules out this entire region. So this single event was enough to exclude this entire theory of gravity, in this region up here. So we were able to completely exclude this entire theory as dark energy. And this was the paper that I received the award for. More generally, what does this mean? So I put up one technical slide for those who know, but for those who aren't familiar with this, let me just tell you about it. So in theoretical physics, or we have a field theory description of dark energy, and you can think about it as a recipe for writing down theories of dark energy. So essentially, this recipe includes some ingredients which are basically free functions that you can put in and choose to write down models. So there's a few of them. There's G5, G4, G3, and G2. And this was kind of a limited theory. It was a theory of gravity which both exhibited the Weinstein mechanism and was a healthy, consistent theory, which is what this means. And what does this test do to it? Well, after GW 1708-17, this line here is completely excluded. This line here up to this factor there is also completely excluded. The others are not, but they're pretty not really considered anyway. This one, even before GW 1708-17, didn't really fit the data very well, the cosmological data. So by itself, it wasn't really considered viable. And this one is actually not a theory of modified gravity. This is actually the first hypothesis that I told you about, that there's some type of new matter there. It fits into the framework, so it's included. But if you just have dark energy driven by this, it's not modified gravity. This remaining term here is actually these classical theories of gravity that I told you about right at the very start, the ones that can be tested in the solar system, so they can't be dark energy because they're constrained by solar system tests. So that was it. We were able to exclude essentially this entire possibility as dark energy, which was great because we want to rule out competing theories as part of our job. But dark energy is still out there, and we still want to understand what it is. So here we are now in 2025, and I just want to tell you a little bit about the current state of dark energy. And really, it's more mysterious than ever. And that's because in the years between, we've had new surveys that have either concluded or are currently taking data and are starting to release them. So we've got the Dark Energy Survey, which has concluded, DESI, which is currently releasing data, and Euclid, which just launched. And they're finding some real extra surprises in the data. So one thing we learned in the last couple of years is that the dark energy is not static, it's evolving. And this is not what we thought prior to 2024. So right at the start of the talk, I told you about this model here. This is called the standard cosmological model. And in the standard cosmological model, dark energy is static. And what I'm plotting here is a 2-parameter extension of dark energy where it's not static. On the bottom, I'm plotting essentially the value today, and on the side is a parameter which tells you how quickly it's evolving. So anything along this, this horizontal line here is static dark energy, and this thing here, this is the equation of state of dark energy for the cosmologists in the room. You're on this vertical line. So the intersection is that model that I told you about right at the start, the dark energy model that has best data since 1998. As of 2025, as you can see, it's no longer included in the posteriors. There's evidence that our best fitting model may not be correct and may no longer accommodate the data. So actually, I guess 2023, not 2024. And so for me as a cosmologist, it is really exciting because I want to understand what dark energy is, and knowing now that it's time evolving is something I'm very excited about because all of the models that I worked on have some amount of time evolution. So I think this is a really great discovery. But it's part of a much broader picture that's emerging. So in the last few minutes, I want to move on from dark energy, and I want to put this into the bigger picture of these, what I call cosmic anomalies. So over the past 10 years or so, there have been hints at this in the data already. There have been what we call cosmic anomalies, or cosmic tensions, sometimes people refer to them as, that maybe our best fitting model of cosmology might not be able to fully accommodate the data. So this DESI result is only the latest in a line of cosmic tensions. And I just want to tell you about a couple of other cosmic tensions because I think they're really interesting and they're worth thinking about. And I'm not the only person who thinks this. If you look at these are all conferences that were held over the last 5 years or so, or 7 years. And they're all called things like cosmic controversies, cosmic crises, tensions, headaches. These things were really unexpected, and people have still not agreed on their origin, or whether they're a signal of new physics, or whether they've got something to do with dark energy, or whether they're just systematics in the data. Let me tell you about them. So I'll tell you about the two most important cosmic tensions. So the first is called the Hubble tension. And the Hubble tension refers to measurements of something called Hubble's parameter, h0, which is a number that measures how quickly the universe is expanding. So not the acceleration, now the velocity. And there are two ways of measuring the Hubble constant. You can measure it locally, and what this means is you get out the astronomical equivalent of using a ruler and measure the distances to galaxies, see how quickly they're moving away from you, and you can calculate the speed. And this gives you one number of h0 that has this somewhat peculiar units over here. Another way is from measurements of the cosmic microwave background, which is an inherently different measurement. It relies on physics in the early universe and how much we know about the early universe. And as you can see, these numbers, they don't agree. The error bars are absolutely tiny because we have such precise measurements now that we can really get the error bars down. And this is a 5 sigma tension. So to put this in context, and I hope some of you in the room might be particle physicists, I'm an astronomer, so I refer to it as a tension. But if I was a particle physicist, I would not be referring it to as a tension. I would be up here telling you that this is a discovery, because that's their benchmark for discovery of new physics. Is it a signal of new physics? Well, we don't know. Here it is in a slightly different picture. So this blue band is the local measurement. This pink band is the early universe measurements measured using different methods. But as you can see, very roughly across multiple different probes and multiple different experiments, this tension is there at differing levels of significance, somewhere between 4 and 6 sigma. One of my slides is unfortunately gone. So I'll summarize what I was going to say in words. There's some discussion or some debate over whether this is a genuine signal of new physics or whether there's some kind of undiscovered systematic in the data. At this point, over the last 10 years or so, we have consistently interrogated the data and reanalyzed it. The latest analysis, I think, was 23. They looked at 70 different data analyses of these systems, concluded there was no evidence for systematics. So I'm personally very excited about the possibility that it might be a signature of physics beyond the cosmological standard model. I'll move on and tell you about a different tension, which is the S8 tension. So this is a tension to do with how structure forms in the universe. So as the universe evolves, dark matter and regular matter collapses to form collapsed structures, and that's what I'm showing here, these cosmic filaments. These are galaxies at the center. The amount of structure formation, of course, depends on what's in the universe. And again, there's a tension in how much structure forms. So it's quantified by a quantity called S8, which I won't go into. But it essentially measures the clustering of matter. And there are 2 measurements. You can either measure it in the late-time universe directly by using things like weak lensing or galaxy clustering surveys, or you can measure it in the early universe using the cosmic microwave background. Once again, there's a disagreement here. I put kind of these tilde signs instead of equals because, as you'll see, the picture's not as clear. But it's a tension of roughly 3 sigma or so. So not quite as significant as 5 sigma. Particle physicists won't tell you they've discovered anything, but it's 3 sigma is enough that people are interested in thinking about whether it's there or not. Here's a slightly more comprehensive picture. You can see these are early universe measurements up here. They all cluster at high values, and you have lower values down here in the late universe. To put that in context, the values in the early universe suggest that there should be more clustering in the late-time universe or more forms than we're observing. So if there is some type of new physics out there, there's something out there that's suppressing structure formation between the cosmic microwave backgrounds and today. This is not as clear-cut as the Hubble tension. It's harder to see what's going on because on these types of scales, you get some very messy astrophysical effects, things like baryonic feedback and things like that. People take this seriously for various reasons. So that's actually the end of my talk. What I think is really exciting about being here in 2025 and what's really exciting about being cosmologists is that maybe there are new discoveries around the corner. We've got all these indications that our best fitting model is not able to fully accommodate all of our observations. And as a theorist, it's my job to think outside the box and ask what types of new physics could fit it. So maybe there are new discoveries around the corner. And as I said, it's an exciting time to be a cosmologist. So I'll stop there and say thank you very much for your attention. Thank you.
Thank you for your talk. Is there any questions? Are there any questions? Maybe I'll ask a question.
Sure.
So this BNS event, W17-17, was observed at LIGO band. Perhaps in the future, LISA, we are looking at different frequencies. Maybe we see something.
I think it's possible to do this multi-band gravitational wave observations. I don't know about these types of events, though. I think it's kind of the brightest, loudest events that would be seen in both bands. I know that the original discovery would have been seen by LISA if it was operational, but I can't comment on this one. But for some systems, it is possible. I just don't know whether it's neutron stars.
So to what level is the screening then effective, for instance, for the strong equivalence principle, because the solar system microscope limit is really, really tight.
Sorry, do you mind speaking up a little bit?
Yeah, the microscope limit on the violation of the strong equivalence principle is really tight. And of course, I was hoped to get 5 orders of magnitude more. But at what point would you be worried about the limits from the solar system to be?
So I think microscope tests the weak equivalence principle, not the strong equivalence.
Then let's take the pulsar limit that we have from a triple system, where if you divide it by gravitational self-identity, it's actually comparable to what the microscope limit does.
Okay. If that's the case, you might be able to get different bounds. I think the problem there would be, you said it's a triple system, right? So these theories are very complicated, as you saw. I think they're some of the most complicated theories that I've worked on in my career. Calculating anything beyond one-body systems here is incredibly difficult. Even two-body systems are really difficult. 3 would be probably even harder. Typically, you need to do it numerically, but in theory, you could do this. So I know there was a group at JPL that they calculated it for the Earth, Sun, Moon system. So maybe it's possible to take what they did and apply it to the triple system. The caveat to that, of course, is that, these theories are very nonlinear. When you change the scales in the problem, maybe the code no longer works, so there's some kind of numerical difficulty. But yeah, if you're willing to try and overcome this issue of non-spherically symmetric systems and code this all up, yeah, that'd be great. It'd be great to have more tests of it. I should say, funny story about that. During this time period, every time I would travel somewhere or meet someone new, we'd discuss the Weinstein mechanism, or sometimes there'd even be people in my own field. And inevitably, we'd start discussing the issue of 2-body systems and 3-body systems. And so, we'd start writing down equations, start doing things in elliptical coordinates, things like that, these kind of adaptive coordinate systems. Every single time, within about an hour or so, we ended up giving up. It's a difficult problem.
Okay, thanks.
Any question?
Thank you. My question is, Desky gravity is just a model of dark energy, right? It's not the. You could have lots of other dark energy model, right? So when you say rule out, so what you're saying is basically you rule out a certain parameter space of this model, but not necessarily.
Yes, correct. So as I said, if you instead want to work with these models, those are not excluded. If you want to work with models beyond this framework, you need to be a bit careful, because as I said down here, this is a framework which is pathology-free. So yes, you can write down other theories, but these theories may not be healthy or self-consistent from a theoretical point of view. And so typically theorists would want to avoid such models and typically wouldn't want to consider them in the first place, just because they're not well-founded theoretical physics models.
Right. So you're saying the more general, or the general model family basically is described by this sets of.
Yes, up to a slight caveat. There's a slight extension of this beyond this thing here. It's called DOST, which stands for Degenerate Higher Order Scalar Tensor Theories. And it has very similar nice properties, like being pathology-free. A large region of these theories were also constrained by this same event. And what wasn't constrained was ruled out by the possibilities that gravitons could decay into dark energy, which is not observed. So these theories, up to a few caveats, are also excluded. The other thing you can do is you can fine tune. You can always fine tune. So you can always take these different terms and tune them to infinite precision to avoid the constraint. You can do that because you can always constrain the sum to be 0. But again, that's not something that theorists typically feel comfortable doing.
Okay. And then link back to the galaxy cluster observation you talked about.
Yep.
So that data, as you said, basically support which part of that Lagrangian?
This one?
Yeah.
Yeah.
Yes. So rule out which part or support which part back to.
Oh, sorry. This part here is
Hodesky
excluded.
Sorry.
This part here is excluded, and this part, the white part, is allowed.
Could you pardon, please?
This part here is excluded, and this part is allowed.
Right. I mean, in terms of those terms in that Lagrangian density.
Yeah, that's a little bit trickier. It will actually exclude a lot of them. So for that test, it won't completely exclude any of them, but it will bound any of these.
Exclude.
It will exclude parameter spaces for these bottom 3 terms here. It won't completely exclude them because you've always got that white region.
Okay, I see. Thank you.
If there is no question, let's thank this.
Thank you.